companies they don't have training programs, for someone to come over and teach basics of seismic wave propagation theory, and the employees or the scientists are expected to know these. Only I've taught this kind of course only at two companies. One was at ExxonMobil, another at ConocoPhillips. So I think the vision that you guys have is quite admiring. So I will basically start, and now you can start to record now. You can start to record now. Okay.
Yeah, yes, sir. It has been started. Yeah.
Okay. So this is my first lecture where I'll go over the fundamentals, very basic ideas, which most of you might be familiar with. Nonetheless, it does not really hurt to revisit these. So in the next few slides, I'm going to show you the motivation behind why we do what we do. So this is a nice example where on the top panel I have a picture of an outcrop. So here you can see different units that geologists are interested in studying. However, they are only available on the surface. So what do they look like in the subsurface? And for that, we make use of seismic data. And a typical seismic volume would look something like this. And right from the beginning, I wanted to warn you that this looks like somebody has taken a picture of the subsurface, but there's a lot that has gone into getting this image from raw seismic gathers. And that is what we will be focusing on. So overall goals of our exploration seismology is basically to aid in geological interpretation. For example, what is the depositional setting? Do we have any structural closure? And of course, for engineering purposes, we have stress orientation, well-bore trajectories, and of course, our ultimate goal is to estimate rock properties so that we can come up with petroleum systems risk analysis. And this also has applications in monitoring CO2 sequestration and for geothermal applications. So seismology has many applications, and what we're focusing on essentially on hydrocarbon exploration, but the theory that you will learn is applicable to all of these different application areas. What contrasts exploration seismology with earthquake seismology is that our method is an active source method. So here we design a field experiment where we actually design where to put the sources and receivers. So these are known. In earthquake seismology, the biggest unknown is the location of the source. And the receivers are wherever they are, because earthquakes don't come with a warning. If they did, that would be nice, but that never happens. So for our case, we have sources and receivers that are known, and we know where we're injecting the source, and we also know the type of the source. So this is much different from earthquake generated waves in the sense that there are many more unknowns in earthquake seismology. And we actually pay attention to a lot of details in those seismic records, and we'll touch upon that a bit later. So detection of these depend on several conditions. So physical conditions, it depends on acquisition geometry. Just because there are physical conditions existing in the subsurface does not necessarily mean that we're going to observe those on seismic records. It depends on how the sources and receivers are placed, and also at the same time, what kind of equipments we have. So if you have any question, please unmute yourself and speak up. Any question, comment?
No, sir, there is no question. Yeah, no, sir, there is no question. And if anybody have any question, then please raise your hand or you can unmute yourself and ask.
I think best unmute yourself because I cannot see the chat box here. Okay.
Okay, okay. Yeah.
Okay. So now that we have planned an experiment, we have put sources and the receivers. What is it that we measure? We measure some wiggles like this, where one axis is time and other axis is the location of the receiver, for example. But this is actually a three-dimensional plot because here what I'm plotting are what we call amplitude or the strength of reflections. So you could make it as a three-dimensional plot, but we're used to making those as wiggle plots, like what I've shown you here. And in an ideal situation, we can put one trace at a time at the surface location, and that gives us an image that looks like this. So in this image, we have the location of the receiver in this particular case. Let's say that this is a single shot, single receiver, and this could be in three dimension. And then we have time here. So as a function of time, we're measuring these reflections, recording these reflection events, for example. But these are not just mere reflections. This could be refraction, transmission, converted waves, and so on and so forth. But what really dictates the strength of these reflections are the contrasts in elastic properties. For example, contrast in impedance, contrast in velocity, and so on. So, like I said, we measure time and amplitude as a function of offset for seismic events. And seismic reflections, they show edges of geologic units, okay? So in other words, they are basically showing you the interfaces. So my colleague actually generated this picture, which is used very commonly in computer science community for image processing. So if you take this particular image and if you have assigned some acoustic impedance like velocity and density, and you can probe it with normal incidence seismograms, you can see what this looks like. Okay. So this is an image of a human body. We're interested in the subsurface. Here we know what the image looks like. In our case, this is a big unknown. So what is it that we measure in a seismic event? We have direct waves, and I'll explain to you what they are. Then we have something called surface waves that is not talked about a lot in exploration seismology. We have diffractions, we have diffractions, we have reflections, we have multiples, then we have, in land case, you have air waves, and you can also see some interface waves. So why do they occur? And this is because the seismic events occur because the disturbance that we create by explosion or some other kind of source, maybe vibroseis, or in marine case, if an air gun, these disturbances propagate inside the medium and they go through different reflection, refraction, and so on when they encounter certain changes in rock properties, and they give rise to the seismic events which come back to the surface that we record. So in order to understand how these seismic waves are affected during their propagation, there are certain properties of rocks that we're interested that we have to know. And these include a lot of parameters. Okay, as you can see, P wave velocity, shear wave velocity, and surface wave velocity is actually sort of a combination. Then we have acoustic P impedance. So another term here would be density, P impedance, shear impedance, and then bulk modulus, Young modulus, shear modulus, Poisson's ratio, and densities here. I didn't notice that. And of course, attenuation and anisotropy. So what you see is there's a whole bunch of parameters that I have listed here. And I'll tell you later as to how many parameters we're interested in, how many parameters actually do affect wave propagation theory, of which how many we ignore, and how many we would like to have. We cannot have an estimate of all of these parameters, but we always, make a compromise and go after the most important parameters. And I will talk about those as we go through different aspects of wave propagation. So here, what we do not measure. I told you what we measure, right? As a function of travel time and space, we measure amplitudes. What we do not measure, and this is what we are interested in, absolutely interested in, are thickness of layers. We want to know the depth of different boundaries because we have to make a drilling decision. We want to know lithology, like what kind of rock types we have. We want to know what kind of pore fluids we have. We want to know porosity, mineralogy, phases. We want to understand the stress regime, pore pressure, permeability, fluid saturation, and temperature. So there's a whole list of items. And these are things that we don't observe. Those are of primary interest. If you go to a reservoir engineer or a geologist and tell them that, this is impedance and this is pure velocity, they're not interested. All that they want to basically take these data and turn those into actual rock properties. So how do we do that? So that's another complication that we have. Okay. The first is what makes up these seismic images. And second is how do we take this information and turn those into properties that are of value? So in order to be able to do that, first we have to see what our wish is and what we actually gather in terms of data. You see, look at this outcrop. And here's the scale here. It's about 50 meters. Okay. And our wish is that we are able to see subsurface in this kind of resolution. But that does not happen. What we measure instead, these seismic traces. So now you can see that a lot of these details are lost in between just maybe a wavelength or two wavelengths of these seismic traces. So that's a big challenge. So we need to understand how this detailed information basically folds into these small part of the wiggle, and maybe then we can hope to get at least some estimate of what's going on even at this scale. The key point is that what we see here is limited by frequency. So this is actually frequency limited. So why is that? When you go to a doctor's office for an ultrasound, you can actually see many of the details in the interior of the human body. And that also depends on what kind of equipment they use. For example, with ultrasound, they can see certain resolution, but then other kind of radiometric imaging, they can see more details. So here, the complication that we have is that we need high frequencies to see thin layers. That comes from basic acoustics idea, right? So you want to see small objects, you need to have high frequencies. The biggest problem is that, well, first of all, seismic wave that consists of a wide range of frequencies travel deeper into the earth. If our wish was, like if we put in a delta function in terms of time and they get reflected from each one of these, then we'll be able to isolate these. First of all, we cannot inject a delta function. It's a finite band of frequencies that we're putting in. And then the second problem is that as the waves propagate, some question or it was a disturbance?
I think it was just a little disturbance, sir.
Okay. Uh, so yeah, so if you could put a delta function and you could propagate through the earth, we would actually see all the details, but that doesn't happen. because we cannot really inject a delta function. Even if we could, delta function basically has wide spectrum, so it has all the frequencies. But then when it propagates through the Earth, Earth acts as a natural filter that removes high frequencies. And so this is basically what we call absorption or attenuation property. So for example, a low pitch voice travels further than a high pitch voice if they are the same volume or amplitude. So you're seeing exactly the same, observing the same phenomenon when it comes to Earth. Finally, what we have to do is to take those images after a whole bunch of processing and then do the geological interpretation. Now, this is where we need to be very careful about how we process the data and how we interpret. Because geologists, given a seismic section, would trust you 100%. They trust geophysicists, and they tend to interpret everything that shows up on the seismic section. So these are some features. They might be interested in mapping, for example, on lap, top lap, some sequence boundaries, and some truncation boundaries, and so on. So here I have a picture. So this is what goes to an interpreter, and an interpreter puts in these marks. Nowadays, it's all done on workstations. But when I started my career, people would have huge seismic sections on their table, and they'd be marking those with yellow markers. Okay. So here, for example, some boundaries, and then dipping layers, and then the faults are marked there. And of course, nowadays, even AI tools are being used to do part of the interpretation. But I just wanted to warn you, geology is very complicated. You cannot substitute AI for someone who has many years of geological interpretation experience, because geologic intuition and geologic understanding is very, very important in coming up with this interpretation. Even for seismic processing, also we need that. So here is another one where somebody is trying to do structural interpretation, different boundaries. And in Gulf of Mexico, our main interest is in salt bodies. And you can see the salt body here. And this is, you can see there is an absence of any kind of reflection through this zone. And what we have here is these are the salt boundaries, and this goes to an interpreter, and the interpreter has to mark these. So this goes through a huge volume of data, and there has been some AI work also on marking the salt bodies with some success. We have structural interpretation where we are interested in marking, say, faults and stuff, structure like that. And we have salt here. But what we are really doing these days is finally we're interested in quantitative interpretation. So we want to go into the reservoir model, and we're interested in estimating certain reservoir properties so that we can have some um, planning for production, and also we can decide on drillings. So so what is it that we're interested in? Say for example, this is a particular zone, could be a sand body. We're interested in, for example, thickness. Okay. Here we are interested in cell lithology. Okay. We'd be interested in porosity. And then we have reservoir properties like fluid saturation. And all these things, all these parameters are very useful when it comes to reservoir engineering applications. Now, do we estimate those directly from seismic data? No, we need to have some well information and rock physics to be able to get to something like this. But this is our ultimate goal. So when I say that from seismic we need well and we need rock physics to integrate these, and there is a mismatch in the scale as well, you see that there's some degree of uncertainty. In fact, there's quite a bit of uncertainty sometimes, and that is something that you have to be aware of. So some of the tools that we have for equipment, we have seismographs, geophones, and hydrophones. These are also called seismometers. For land applications, we use survivor size, explosive. In marine case, we have air guns, marine streamers. Some nowadays we're using fiber optic cables, and of course, computers. I can't stop mentioning how important computers are. So part of what we do makes use of signal theory, signal analysis, or digital tools. See here we use Fourier transforms, sampling theorem, frequency, different estimates, signal analysis. Convolution is a very important uh, processing step, and that can help us a lot in seismic data analysis. We also use autocorrelation, cross correlation, and so on. And some of the basic algorithms that we use, which I'm not going to talk about, velocity analysis, NMO correction, stacking, migration, deconvolution, Q compensation, gain recovery, normalization, and so on, and filtering to a certain extent to get into the right frequency band that we're interested in, where the signal to noise is high. And finally, you'd like to get something called seismic attributes for interpretation. So this is how actually it goes. Seismology basically teaches us the physics of wave propagation, and equipment basically tell us how we record the seismic events. Acquisition, where we set up field geometries, we can collect land seismic data or marine seismic data. And it's very important to make sure that your experimental design is adequate for your goal and make sure that the field setup is done right. And then in processing, we apply different kinds of algorithm first to fix problems in the data and improve signal to noise ratio. But the ultimate goal is to develop a depth image in 3 dimension and also come up with rock properties that I showed you earlier. So in inversion, we have different ways of running inversion, or rather making use of different kinds of attributes. And you hear different names for inversion. For example, AVA, amplitude versus offset, or amplitude versus angle. Then we have tomography, and then the holy grail is full waveform inversion. So these methods differ in the way they use the data and the way they approximate the physics. So for example, for AVA, we use NMO corrected angle gathers. So here the focus is only on amplitude. In tomography, we use travel times only. In full waveform inversion, we try to include as much information from the shot gather as possible with minimal processing of the shot gathers. And we don't apply NMO on the shot gathers when we're running full waveform inversion. So for AVO, the physics that we use is simply reflection coefficients, which is given by Joupler's equation and convolution model. And of course, we use an optimization method, it's typically local optimization. In tomography, since we are matching only travel time, we use ray tracing kind of ideas using Eichner equation, which we'll talk about. And again, we use some kind of local optimization like gradient descent. For full waveform inversion, we use full wave equation, which we try to solve using finite difference or finite element. And in fact, the focus of the first module of this is basically to talk about go into details of wave equation and how we actually solve it. And you can use mostly local optimization, but nowadays we're also using some global optimization. And in all of these, we need to also think about uncertainty. And of course, I don't have time to go over uncertainty methods, but this uncertainty quantification is one area where the industry is focusing quite a bit nowadays. And for that, we use things like MCMC and some other methods. Okay,
And
so
sir, one question,
yeah,
sir. So,
yeah,
sir,
please.
where does that kinetic equation and those what we call scattering wave theory fall? Does it come under FWI or is it some different category?
Yes, it comes under FWI. So wave
Okay,
equation and their solution. This wave equation can be solved either in 1D or 2D or 3D. Okay,
okay, okay.
depending on that. Yes,
Uh,
and you will see the sequence when I talk about these different methods. Okay. Okay, and now so the complete interpretations needed to help define petroleum systems, which include source, seal, reservoir, and geologic history. And this is not done in silo. It basically is done by a team comprising geologists, geophysicists, and maybe even reservoir engineers. Okay, so they integrate all kinds of data. And of course, you are in those of you who are in Reliance office, they have access to big, visualization, and you can essentially fly through the seismic data. So this is how a typical field setup looks like. All right, now this is a synthetic shot gather um, for a land experiment. So how many of you can identify what these different arrivals are? Anyone wants to name what these are? Because this is the first step. Given a seismic record, a geophysicist is expected to understand what information you have there, right?
So we
Anyone?
have the ground rolls. That's very near evident.
Mm-hmm. And what is
And,
this?
and this is airwave is there. The low frequency stuff. That should be, I think, is
That's
the
the
airwave.
direct arrival.
That's a direct arrival. Good. But how do you know this? Because you understand how the waves are propagating, right? So I can mark this. You have direct waves, you have first reflection, you have second reflection, you have third reflection. These are different layers. And then you have this should be the arrow should be here. And then we have some air waves. You're absolutely right. Now, if you look at so these are the these are different markups, and so this basically tells you that there are some uh, interfaces. What this one does not have, this synthetic example, very simple. It does not have any internal multiples or converted waves. Okay, and we'll talk about all of those. So, real seismic data. Okay, this is land seismic data after some processing of the data. This is one of the good quality data sets. And you can see all of these linear events, and this is fairly large offset. So what you see, in addition to reflections, you also see refraction, turning rays. Okay, and they have linear features. So you have direct wave that has a surface wave that has been actually marked here, and so on. Okay, marine data. From here, what can you say about the depth of water? What can you say about the ocean depth?
It's ultra.
This is a
It should
stream
be
of,
an ultra deep water. Yeah.
yes. What is the depth? Do a back of the envelope calculation. How
It's
would you
near
go
about,
about?
Around 2200 meters, something around that.
yes,
Yeah.
2000.
Yeah.
So this is basically your first reflection from the seafloor, right? So
Yeah.
from there, what velocity did you use, Ashok? To tell
1500.
1500. That's typical water velocity, right? And
Yeah.
here you are actually seeing some multiples also. Okay. So direct wave, primary reflections, and multiples, and then these are refractions or turning rays, and these are very very important in, say, for example, FWI and for velocity model building. So In earlier days, people would mute out all of these information. Okay, because if you actually try to understand these large offset reflections, refractions, elastic effects, anisotropic effects, they also start to come in. And we didn't want to, it's not that we didn't know how to handle those, just that we didn't want to do this because it's very expensive. So the physics, what you see here, if I go back to this slide, what you see is that as you go from left to right, you're seeing that we are actually, how is the physics changed from left to right? It's more complete physics, right? More and more
Yeah.
complete physics. So how come we were using approximate physics for a long time? Even now it's approximate, but it's less approximate than what we were using earlier. What else changed? What changed here is compute power, right? So we can see that when the computers become faster and faster, we become more and more ambitious, and we try to bring in more information from the subsurface by bringing in more complete physics. And that is possible because we have much faster computer now than some 30 years ago. Okay, so that was our marine data. So in summary, seismic waves carry encrypted information. So what you get from the recordings of seismic data are not directly subsurface image, but there is some degree, there is some kind of encryption into it. So can we understand the encryption? What kind of encryption? For example, when there is an encrypted message received by, say, some CIA, or then what they have to do is to decrypt it to understand what's in there. So to be able to do that, they have to understand the encryption. In our case, we have to understand wave propagation theory. So modeling and understanding of wave propagation theory basically tells you how the waves are encrypted when they come back to the surface. And this is what we're going to focus on in the next few days. So finally, can we depict the wiggles to reveal subsurface structure and rock properties? And that is our inversion. Okay. So to understand encryption, we make use of what is called forward modeling. Okay. And to decrypt the wiggles, we have to use inverse method. Okay. So we will focus on this for the next few lectures. And so this is kind of a general agenda for what we're going to talk about. And here we talk in detail about wave equation, viscoelasticity, Green's function, and so on. We'll talk about travel time and ray theory. We'll talk about Taupi transform, convolution model, reflectivity, Kennett approach in detail. We'll talk about finite difference, and we'll also talk about a scattering theory approach. Okay, and in between, I'll try to give you some assignments and some notebooks to create for computing some of these.
So one question,
So
sir. In the
yeah,
marine short data, what you showed. So can
yeah,
you, sir, also talk about diving waves where they will fall? These are essentially the
yes,
refractions, right, sir?
yeah. So these are the diving waves.
Okay.
So that's what happens is that for those of you who may not know what is diving wave, what we have here is you know typically in reflection seismology, what we have been using is a model, a layered model. Okay, and we say that each layer has a constant velocity v1, v2, v3, v4, and so on. and they give rise to reflections. However, when there is a contrast in velocities such that v2 is greater than v1, then you have a critical angle. And in critical angle, what happens is that we have what is known as head wave. Okay. Now these head waves are very weak in amplitude. Okay. And they basically follow nearly a straight line path, which is with the velocity of the lower layer. Okay. So if you draw a seismic trace, you have this reflection, and then you have this head wave. Okay. However, what we need to understand is this really a head wave? Because head waves actually have very weak amplitude. So what we have here, uh, instead, when you go into details at a large offset, is going from V1 to V2 is really not, this V2 is not a constant velocity layer. It can have a gradient. So if you plot your velocity model, V as a function of depth, maybe your first layer say is water layer, then there is an interface, then there can be a gradient, and there can be an interface, there can be homogeneous layer, there can be another gradient layer. So the gradient layers, within the layer, there is, in theory, there is no reflection. Of course, there can be some higher order reflectivities, but let's not talk about that. So what happens here is that the rays actually turn. Okay. So why are we seeing such linear features? Now, one of the things that happens is that when it changes, the gradient is very sharp. What you're seeing is that multiply reflected turning rays. And they tend to come with a velocity that is similar to the head waves. And that's what actually would give us much better constraint of the velocities. Okay, and that is why these diving rays are important. Okay, and the reason they're called diving rays is because they just dive, right? They just turn around. Okay.
Okay.
Any question?
And why they are important, sir, in FWI?
Well, because they give you the background low frequency velocity models
Okay.
much better. Yeah. So
Okay.
sometimes what we do is simply mute this part and run an FWI, and that gives us the low frequency model, and then we bring in the reflections.
Okay.
Okay.
Yeah.
So
Understood. Thank you.
yeah. Okay, so this is roughly the plan for this few days, and of course, this is a rough plan, and I'll see how the lectures goes. Like some days I can probably bring in more topics, some days less topics, but in the 5 days, the goal is to talk about different aspects of seismic modeling, wave propagation theory, using different ideas. So here for today. After this introductory session, I will talk about some basics of elasticity, and there'll be some maths. I hope you put up with that and try to understand, because I'm not gonna do a lot of derivations. I'm just gonna focus more on the implications of those equations and how they apply in your understanding of seismic data. So today we'll talk about elasticity basic, linear elasticity, waves and wave equations. This is very important. And you hear people talk about, oh, I'm using VTI, I'm using TTI, I'm using acoustic, I'm using elastic. So what is the difference? Where is that difference coming from? That's what I'm going to talk about. And then, of course, we talk about anisotropy. This has become very, very important nowadays. And then, so start with some solution. First, what are the equations that we want to understand for understanding seismic data? Then just given the equation, we may not, given just the equations themselves are not useful until we solve those, right? That will give us then insight into what can be expected in those wiggles. So we start with very simple analytic solution for a homogeneous medium, and we call that Green's function. And the Green's functions are important because they are basic building blocks for going into more complex wave propagation phenomenon. And you'll see those when we talk about different approaches, particularly, say, when we talk about Born series, okay, and Kirchhoff method, and so on. So that is kind of that ends the first lecture, and take a short break, about 10 minutes. Can you see my screen?
Yes, sir.
So I'm starting now, okay?
Yeah, yes, sir. Yeah.
So you can start recording.
Yeah. Okay.
So let's look at some of the basics of elasticity in this lecture, like I mentioned earlier. And here, it all starts with our data, right? We have this particular model. In this case, um, I have this subsurface model from Gulf of Mexico. This is a salt body. And we have a shot and a bunch of receivers. And this is what the shot gather looks like, one of the shot gathers, when the receivers are everywhere. And when the geology is very complicated, it's very difficult for us to go and identify each of the reflections, refractions, and point out what they are. And this is where we need to understand how this got generated given this particular model, and how different this is going to look like if the model changes. That is the theory that we'll talk about. So we do the seismic experiment, and here we apply certain external forces, and these are called stress on solid materials, and the deformation is called strain, and I will mention what they are. I'll go into a little bit detail of those. And we use a theory of elasticity. That is, we use that for studying the wave propagation of such disturbances through the Earth. And a perfectly elastic solid is one that returns to its original shape once you remove the force. So an explosion source is what we used in seismic exploration. And this could be an impulsive stress, or it could be sort of a charge in a sort of short hole, and so on. Now, so let's look at very basic elasticity, which you probably run in high school physics. We have this spring, and then we're adding mass. So here we have, when you have 100, this is going to 3.7. The 400 is 15.3. So this is the basic idea behind elasticity. And if you plot essentially mass against the extension, what you see is a linear trend. Okay, and this can be fitted by a straight line. So this is your force, and this is your extension, and this is your proportionality constant, because F is proportional to X, and we learned that in high school physics. So seismology is actually built upon this idea. It's a very basic high school physics, just that we have to deal with it in 3 dimension, and that is what makes it a bit more complicated in terms of the kind of math we do and the kind of experiment we do to verify those. So starting with this, we'll first talk about continuous medium. So when we're doing a seismic experiment, you can say that it's behaving like a spring and dashbar, but in reality, we have ground motions that are set up by explosions or earthquakes. So it's a time-varying deformation in material media. So all material substances are composed of atoms, and which may be forced into vibrational motion. So we have to make some assumptions here, and that assumption is of a continuous medium. So in reality, what we have is a whole bunch of discrete atoms. They have bonds, and there's mostly empty in between them, and there's no smooth field that exists at this scale. So this is what we can call it a microscopic scale, but we are interested in macroscopic scale, or continuum hypothesis. So the same body can be treated as if every point has a well-defined density. And of course, then we'll talk about stress and strain. So what you see here is the color gradient roughly to show you how the stress is varying. So essentially, in this box, what we have is an average of all of these detailed properties. Okay. So now this becomes more like what we call particle, and we can say that the particles are moving and they are connected. So in reality, though, if you go into details of that and the atomic scale, that is not the case. But this is what we use a continuum model in developing the theory of seismology, which is essentially a part of continuum mechanics. So this representative volume, basically pick a small chunk, delta V around some point x. So it must be large enough to contain enough atoms, but small enough that the macroscopic field does not vary much across it. Okay, so this is very, very important. And I think to some extent you can think in terms of frequencies also. And of course, we'll go into some of the details later on. So this is the basic assumption when you build the model. Okay. So a continuous medium is within each particle atoms move in unison. So all the atoms are moving together. So the theory of seismology deals with macroscopic phenomena, and it is formulated as if the matter were in a continuum, just like the figure I showed you in the previous slide. So we assume that our medium to be a continuum. All mathematical functions entering the theory are continuous functions, except possibly at a finite number of interfaces separating the regions of continuity. This is a very important statement when you are building up the theory or theoretical understanding of wave propagation. So this concept then allows us to define stress at a point, which is a geometric point in space, which is conceived as if it's occupying no volume. And this allows us to use calculus to predict the behavior of deformable bodies. Okay. So now, based on this assumption, we'll define the stress at a point, but in reality, it's really not a point. It's an approximation of a volume. So we'll talk, like we just talked about continuity. Material is continuous if it completely fills the space with no pore or empty space. Homogeneity. So a homogeneous medium has identical properties at all points. And isotropy is the material is isotropic with respect to certain properties if these properties are the same in all directions. So that means that the properties are not dependent on the direction. Okay, now to understand the theory of stress and strain, we have to review vectors and tensors. And like I said, I'll try to make it as simple as possible. We need to describe these properties as a function of position and orientation of the observer. That's why we need to know the coordinate system. That is why we need to understand what vectors are and what tensors are. And this vectors and tensors, these are just tools for describing some of the physical phenomena, physical parameters. So because we want to understand the position and orientation, all the physical laws are vector equations or tensor equations. As soon as we talk about these, we have to think about a frame of reference. Okay, so what kind of coordinate we're talking about? Now, this coordinate system can be anything. It could be rectangular, it could be spherical coordinates, could be cylindrical coordinates. We will mostly do Cartesian axis system, which is basically rectangular, but a lot of the discussions that we have, a lot of the equations, they will be basically equally applicable for other coordinate system as well. For studying spherical Earth, we normally use spherical coordinates. So in three-dimensional Euclidean space, vector quantities are entries possessing both a magnitude and direction. So a vector has a magnitude and a direction. A scalar does not have any direction. And a vector is defined, say, for example, by some basis vectors. Okay, x1, x2, and x3. This could be x1, this could be x2, x3, x3. Sometimes we use x, y, z, and so on. And these basis vectors are normally they considered these are orthonormal basis. So we basically use orthonormal basis function to define the space. I will follow Cartesian axis system. So I don't know if you're able to see this, but let me go. And here, so if you have a vector x, we can write this as x hat x1 plus x hat x2 plus x hat x3. These are the basis vectors. And x x1 hat, x x2 hat, x x3 hat, x, you can call it x2, let's just call it x3. This is x1, I'm sorry about that. So you can write this as x1, x, xi hat. So this is pretty well understood, and you know how to basically take a dot product, and you also know how to take a cross product. Okay, so this is a scalar, and this is a vector. And then there is one other identity that we use quite a bit. So we go from this notation to indicial notation. Okay, this is called indicial notation, where the sum over repeated indices is assumed. We'll make use of Kronecker delta. This delta ij, which is equal to 1 when I equals j, and is 0 when I is not equal to j. And then we also use this cross product formula. Main reason I wanted to just give a brief one slide summary of vectors is that we'll be dealing with quantities that are a little bit more complicated. So you have a scalar, no direction. You have a vector, one direction. What if there is a particular variable or particular parameter that depends on two directions? Okay. So if they depend on two directions, then you can write those as x and y, right? Side by side without any dot or cross. And this is generally called a dyad. Similarly, you can have x, y, z, that is called a triad, and so on. Now we do have some quantity like stress. And although I have not defined what stress is, I will when we talk about that, you will see how this applies to that, how this concept applies to stresses and strains. When I have a force, I know that I can represent it by some amplitude, let's call it magnitude of f, and some direction f, right? And this can again be decomposed into three different components. So similarly, if I have a tensor of rank 2, when you have two directions, it's called a tensor of rank 2. Let's call this A. Then you can write this as Aij, Xi hat, and Xj hat. So these are the two directions that it depends on. Similarly, for third and the fourth order tensor, I'll write 4 bars here. It is elastic tensor. You will see thatCijkl, Xi hat, Xj hat, Xk hat, and Xl hat. That means it depends on 4 directions. So that is the main reason behind using these. You don't have to know anything more than that to understand this, and there are certain operations that we do. So now it turns out that when you talk about isotropy and anisotropy, I don't think this is talked about in any of the seismology books that I have seen. Essentially, isotropic and anisotropy concept comes from tensors. So tensor is said to be isotropic if its components with respect to some coordinate system do not vary when either the coordinate system or the medium is rotated. Do you understand what I'm saying? There is a particular tensor, and we call it isotropic because if you if you rotate the coordinate system rotate the medium, the properties are not changing. This exactly fits into our understanding of what isotropy is, and otherwise we call it anisotropic. So isotropic tensor of order 1 is basically a null vector, okay? Because if you change the direction, the vector always changes. Isotropic tensor of order 2 is your delta function. And isotropic tensor of order 4 is given by these combinations. This is a general fourth order isotropic tensor, and it's a combination of these this conical delta or delta ij and delta kl. Now it turns out that without even talking about elasticity, you can see how isotropic elastic tensor looks like only in terms of like these parameters.
Sir, I have a question here, sir.
Yeah.
So, sir, isotropy, what we understand is something which property doesn't change with the direction.
Right.
But again, we are talking about isotropic tensor of order 2, where you have two directions. So there is something very
So there are
counterintuitive.
some isotropic tensors that may not actually change in direction. So this is true because you have a second order tensor, but you can rotate it in such a way that a new coordinate system, if you write it, then it does not have that. There is a particular type that goes. So this is delta ij is a specific case of isotropic tensor, which is given by this. Okay.
So can we relate with any physical quantity with which, let's say, isotropic tensor of order 1? What kind of physical quantity represent, or an example of that?
Oh, that is there is no isotropic tensor of order 1 because it's a vector, right?
Okay. Okay.
So that's what I said. So here it says the isotropic, if you change the coordinate system, then it does not vary.
Okay.
Okay. So it turns out that there is a special case of isotropic tensor of order 2 where it may become isotropic. Okay.
Yeah. Great.
Similarly, there is an isotropic tensor of order 4 that may become like this. Okay. So essentially what it means is that after applying certain rotations, you can get some symmetry in the system. And we will touch upon that's a very important question you have asked. Like when you go from totally, say monoclinic to orthorhombic, monoclinic, triclinic, orthorhombic, hexagonal, VTI, TTI, HTI. These are all by changing the axis of rotation. Okay, and Eulerian description or Eulerian description is of whatever particle happens to occupy a particular spatial location. So here actually the system moves with the particle. Now we're talking about small motions in seismology around the equilibrium, and we'll show you that we're using linear elasticity. So that makes sense to use Lagrangian description. And on all the mathematics that we do, we use Lagrangian system. So like a seismometer or a geophone records the motion of a particular part of Earth, and it essentially is a record of Lagrangian motion because the particle does not move from its original position. Okay, so we start with a simple one-dimensional strain. So you have initial length L naught, and the new length is L. So the displacement is L minus L naught. Now it turns out that we have different definitions. One is engineering strain, which is L minus L naught divided by L naught, where U is the difference. There's a Cauchy strain, which is L minus L naught divided by L. And there is a logarithmic strain, which is natural logarithm of L over L naught. So each definition, the reason I'm mentioning this, some of these details is because you'll see in different literature, they mention this and we sometimes get lost as to what they're talking about. So each definition satisfies the basic requirement that strain vanishes when L equals L naught. Here, when they're equal, it's equal to 1, so ln of 1 is 0. So when there is a small displacement, then your Cauchy strain and engineering strain, they become the same. So here is a plot of certain experiment. This shows you logarithm strain. This shows you engineering strain. This shows you Cauchy strains. And when this becomes small, which we're interested in, there's no difference between Cauchy and engineering strain. Okay, so we need to talk about this in 3 dimensions. So this is what makes it interesting for seismology. So here, this is say one experiment, 1D representation. This is an extension, and you can talk about these 2 points, A and B, and here we have this difference. So in 3D, you can represent these as vectors. So this is your x that has gone to delta x, and there is u that has gone to delta u. So now you can represent your engineering strain like this, and now we can look at different components of displacements. du1 equals this from basic calculus, and this is when you use initial notation I. So what you see here is that this f is del ui del xj, and you can write this as ui xj, where this ui is basically represents del xi, del something like that. Okay, so del ui del xj is ui xj. Okay, so ui is this, and x is the short form for this particular case. So now this is your epsilon delta x for 1D. So in 3D, you can write ui xj is equal to this, and we only keep the symmetric part, and this is your epsilon ij. This is equal to epsilon ji, and you can see that this is a symmetric. You can call it a matrix in coordinate system here, and we call that tensor because now you have 2 directions associated with it. One is the direction of the coordinate, another is the direction of the deformation. Okay, and that is why you have 2 indices, and that is why this is a second rank tensor. So if you were to write epsilon in actual notation, then this will be like epsilon 1 1 x1 x2 x1 hat x2 hat epsilon 1 2. This is x1 x1 hat. This will be epsilon 1 2 x1 x2 hat plus epsilon 1 3 x1 hat x3 hat. Or in general, you can write this as epsilon ij xi hat xj hat. Okay, so this, depending on the convention that you use, this could be the coordinate direction, this could be the displacement direction. And so now we can write this whole thing in vector notation, which looks like this. So essentially, you can write your strain in this Cartesian axis system. You can write this strain as a matrix where you have epsilon 1 1, epsilon 1 2, epsilon 1 3. Then you have epsilon 2 1, which is equal to epsilon 1 t, because this is a symmetric one. Then you have epsilon 2 2, epsilon 2 3, and then you have epsilon 3 3. Okay, so that's our strain given a particular direction and the direction of the displacement. And but simply stated, this is essentially nothing but deformation. It's a measure of deformation of the body. So here we also look at something called volumetric strain. And the way we calculate it for 3D is essentially sum of the diagonal parts of the strain matrix. And if you look at this, this is your volume, and this is the volumetric strain would be your entire volume has changed. And the reason we like to understand this particular form is because we're trying to understand the wave propagation phenomenon. Okay. And similarly, we can also have rotational strain, which is given by this particular rotation tensor. And so if I were to ask you, what is a strain? Strain is essentially a measure of deformation. And in terms of the actual physical variable, it can be described as a tensor, which has 2 directions. One is the direction of the coordinate that you are measuring, and the other is the actual direction of the deformation. Okay, so given that, we also identify that the strain tensor is symmetric, and we can also think about volume strain and rotational strain. Okay. Okay. So now we come to stress. It's not complicated because everything boils down to your high school physics, just that you're thinking in terms of 3 dimension now. Now we analyze internal forces acting mutually between adjacent particles within a continuum. Okay. So this concept of continuum is very, very important. Remember, I have this volume, then I have, let's say this is my continuum represented by a point. This is another represented by a point, and so on. So now what we're interested in, what is the force acting between those? Okay. So first of all, we define a term called traction, which is a force. And this is a vector because it basically has one scalar magnitude and one direction. And it becomes, since we're talking about the volume, we need to define this force acting per unit area across an internal surface. So that basically quantifies the contact force or force per unit area. And you should note that the forces acting upon particles in a solid or fluid medium, they consist not only of the contact forces between the adjacent particle, but the forces that are not adjacent. Okay? And the forces due to the application of physical processes external to the medium itself, there can be some other forces being applied to the medium. Okay, so if you have a force at a particular point, you can write this as simply a delta function in space and time. Okay, it's point force. So now in the whole volume, if I integrate, this is the basically balance of forces, and that gives us this equation. And I will go into slightly more detail later on. So why are we talking about force per unit area? Here is a nice cartoon. You have two blocks of different cross sections. So intuitively, you can tell that the effective force that is being applied to these blocks are different depending on the shape or size, right? Smaller one is going to deform a lot more than the other. Intuitively, you can say that. And because of that, we deal with not just force, but force per unit area. So now, what you need to recognize is that, so is the stress now a vector? It is a force, right? Is this a vector? Can somebody say yes or no? What do you think?
Yes, stress is a vector.
Okay, anybody else? So what is the difference between force and stress? Stress is a measure of force per unit area, right? So now the question comes in. We can say that this is a vector if area was a scalar, right? So is area a scalar quantity? Anybody?
I think area is a vector.
Area is a vector. Why is it a vector? Because it depends on which cross section you were looking at, right?
Right. Yeah.
And we need a direction to identify that. So if you look at the reason we call it, let's say that this is my area, right? How do you define the area? By its normal, right? That's a vector. If the
Right.
if the area was like this, then the normal changes, right? So
Yes.
this is the stress is a second rank tensor because it has two directions associated with it. One is the direction of force, and the other one is the normal that defines the orientation of the plane, right?
So, sir, we can say that tensors are mostly combination of vectors.
Yes, exactly.
Yeah.
So it's more than that. Combination of vectors in the sense that there are some fundamental directions associated with it. It needs two directions to define uh, particular quantity, in this case trace, and that's why it's a second rank tensor. If you need three directions, it's a third rank tensor. If you need four directions, then it's a fourth rank tensor.
Okay.
Okay.
Yeah.
Okay. So here we have this particular picture. So we like to decompose our stress into normal stress and shear stress. So normal stress acting perpendicular to the plane, and shear stress would be along the plane. Okay. So this is your total stress, and this is your normal stress, and this is your shear stress. Okay. And you hear people talking about shear stress, normal stress, when it talks about geomechanics, earthquakes, and things like that. And this is exactly what it is. It's very simple. So in general, let's say if I take a three-dimensional cube, on each face, I can define different components of my stress tensor. So what I have here, let's say that I have an X, Y, and Z coordinate system. So now for stress, I have two directions. One is the direction of the force, another is the direction of the normal. So this gives you depending on the convention, sometimes people use the first index to be the force direction, the second index to be direction of the normal, and so on and so forth. So in this particular example, what I have is, in this case, the normal to this particular plane is x hat, right? X direction. So the three components of stresses would be tau xx, tau xy, and tau xz. Similarly, this will be tau zx, tau zy, and tau zz. And similarly in the other case. So you can write this now as tau xx, tau xz. So in tensor notation, you can say that this is the component and these are the two directions. And you can write this in this particular matrix, which is tau 11, tau 12, tau 13, or tau xx. It doesn't matter if it's 1, 2, 3 or xyz. And you don't want uh, and this is a symmetric tensor, and you can show that. So because of that, we have only 6 components. So strain has 6 independent components, and stress also has 6 independent components. And stress and strain both are symmetric. Now we use sometimes direction of principal stress. So one of the so if you write this stress tensor as this matrix I just showed you, one of the property of symmetric matrices is that they may be diagonalized. So the transformation from non-diagonal to the diagonal tensor requires transformation of the coordinate system, and a particular axis system you can transform it to. And in that case, you get a matrix that looks like this, and these are called principal components, and the components are along the principal axis, where the shear stresses are equal to 0. The reason that's important is that different kinds of faulting mechanisms are described using the principal axis of symmetry. For example, here you have a normal faulting. In this case, your S2 SH mean is the maximum horizontal stress. SH max is the maximum minimum horizontal. This is the minimum. This is maximum. And then what is the magnitude of these three principal components? You can have a normal fault, you can have a strike slip fault, or you can have a reverse fault. Okay. Here is the effect of stress. You can see how the formation has folded. You can see how they have faulted. So this is a nice example from structural geology, and they understand in detail the stress and strain tensors to understand the structures of different formations. So this is another one for faulting, and then we can also look at these Coulomb failure criteria, which I'm not going to talk about. Okay, so here we actually so far we talked about only this part earlier, right? But if you kept on increasing the stress, then what happens is that it actually is no longer linear. This can bend, and then finally bend backward, bend even so more strain is decreasing, and this basically is a point where you have a failure and rupture point. Now we don't worry about those regions because we are staying within small forces and small displacements, so we can actually only focus on the linear form of elastic region. And that's what I'm going to talk about next. So we understand stress here. We understand strain here. And now we'll look into detail of linear elasticity, okay? Which goes to the next set of slides. But before I do that, I want to derive one important equation, okay? Fundamental equation of seismology. So if you consider a vibrating material of an arbitrary shape, and that has volume, say, delta V, in 3D, I cannot draw it, and then the surface is set delta S. So here, you can sum up all the forces on the surface, simply taking the dot product of the stress, which is a second rank tensor, with n. Now, this is one important thing that I didn't discuss. So, for example, if you have a vector A, and you say that I have this as AX, X hat, AY, Y hat, plus AZ, Z hat. If you take a dot product with respect to this, it will give you AX because other two directions are diagonal, orthogonal to it, so they go to 0, right? But you can take a component, scalar component, in any direction by dotting it with that direction. So you can do the same thing for stresses. So I have a stress, tau, and I can write this as tau yj, xi hat, and xj hat. So this will be a matrix. This is just one line, but so if you take a dot product of tau with respect to some another vector, it will give you scalar, right? A dot product of a vector with another vector gives you a scalar. Sorry, a second order tensor dotted with a vector will give you another vector. So you can see that this went from second rank tensor to first rank tensor. Okay, and a first rank tensor when dotted with another vector gives you a scalar. Okay, so this will give you the force then, and once you because you're dotting it with the direction of the normal. So now Newton's law says that you have to sum up all the forces, the balance of forces. So this is the surface force, this is the force in the volume, and this is equivalent to your mass times acceleration. Okay, integrated over the whole volume. If you did that and do this algebra, what you get is this. Divergence of tau equals rho delta t square f. And this is the equation of motion. And this is also called linearized momentum equation. And essentially, this is your Newton's second law. F equals ma. Balance of forces, okay? Now remember this. We will show you how important this is, okay? Okay, so I'll go to the next slide set. Now, some of the interesting stuff. I hope you were with me and you were able to appreciate little steps that we are taking to get to wave propagation theory.
Sure, sir. Yeah.
Okay. So this is our basic concept, a basic idea that we want to move with. We are going to be within this linear regime. So we saw earlier that we had a relationship between force and displacement for a simple 1D case, right? So we'll need to now look at this whole thing in 3 dimensions. So Hooke's law. And Hooke's law basically relates stress to strain, and we are familiar with this from very basic high school physics. But we'll look at it in a new form in 3 dimensions. So for small deformations, it has been experimentally observed that strain is directly proportional to applied stress. So as you increase deformations, as you impose increased deformation, the relationship between stress and strain becomes increasingly nonlinear. However, we are going to stay within the linear regime. What that implies is that beyond this limit, the medium deforms permanently. And this region is, when it deforms permanently, this region is not of interest in exploration seismology. Okay? Okay, so we have this beautiful force and displacement for the spring that we saw. And we saw that we need a proportionality constant, and this is called a spring constant, right? Now the same thing I want to write in 3D using stress and strain tensors now. So I have tau, which is a second rank tensor, and I have epsilon, which is our strain tensor. Now, first thing that we want to be reminded of is that the amount of deformation that we see by the application of stress is not the same in every material, right? It depends on certain properties of the material. And what is that? So stress is proportional to strain. So now I need to have some constant here, just like I had a spring constant in 1D, right? So what is that going to be? Well, now I have tau ij, and I have epsilon, say, KL, right? In different directions. So if I want to have a constant here, that needs to address all 4 directions. So it means that this constant, which we call elastic tensor or elastic stiffness, this is actually what rank tensor? This has now 4 directions, right?
Fourth
To
order.
associate.
Fourth order, sir.
Yeah, it's a 4th order or 4th rank tensor. Okay.
Yeah.
And so the way we represent it now is This is a fourth rank tensor. Sometimes we write it like this with 4 bars in it. And that is CIJKL, and there are 4 directions. Okay. So we also use this notation, which is the double dot product. Now remember, a dot product between a vector and another vector is a scalar, right? A dot product between a second rank tensor and a first rank tensor or a vector is a vector. So similarly, a dot product between a fourth rank tensor and the second rank tensor would be a second rank tensor, which is the stress. So similarly, we can also define strain in terms of stress, and this S is called a compliance tensor, which is essentially inversion of the fourth rank tensor. Now this is a very interesting topic, which I don't have time to go over as to how you actually invert a fourth rank tensor. But this is what gives you compliance. And those of you who have worked on fractured media, you can see that a lot of times we talk about fracture compliance and so on. So this is our basic equation. So 2 equations we have learned. One is Newton's second law, and another is our Hooke's law. And Newton's second law of motion and Hooke's law, are these new to you guys? No, right?
Yes, sir. Yeah, yes, sir.
They're not new. You have learned it since high school, right?
Yeah, yes, sir.
So all that we have here is a bit fancier representation of those, or rather a bit more complex way of representing those, because we're talking about 3 dimensions. And those
Right,
are the fundamental equations of seismology. Yeah. However, there's one other thing that we ignored, which is damping and attenuation. So the medium that we just considered for constitutive relations do not have any internal energy losses. Okay. So what that means is that the waves would propagate through this medium without any attenuation. And in reality, that does not happen. There's some kind of damping that happens, which happens in a complicated manner, and that depends on temperature as well as frequency and the type of vibration. A simple way to introduce damping term is from the physical analog, where we have a spring and a dashpot. So what we do here is that we say that damping is like putting in a viscous element with response that the force is proportional to the time derivative of the displacement. So now the total force is the spring term and a damping term. Okay, so the spring term is the force is directly proportional to displacement, and in this case it's with respect to the derivative of the displacement. So when we write it in our 3-dimensional space, we have second rank tensor. This part is the pure elastic part, and this is our damping part. So here also we have a fourth rank viscosity tensor. Okay, and if I want to write this in compact notation, the extra term that I have is the time derivative. What it means is that it's basically making use of the strain history, okay, with respect to time. So this is your viscosity fourth rank tensor, and this is your elastic fourth rank tensor. Okay, this is how in most general way you can actually put it in this form. Of course, we make a lot of approximations. So this one is your pure spring effect that we're talking about, and this is spring and dash part, and this one has this attenuation damping. Okay, now let's look at our fourth rank stiffness tensor or fourth rank elastic tensor in a bit more detail and see how we can go from there to different kinds of medium like elastic, isotropic medium, elastic VTI, TTI, and so on. Again, I will not go through each one of these derivations, but they are in here, and I'll also send you some notes. So this is basically our Hooke's law, right? Generalized Hooke's law, the fourth order elastic tensor, and there are some symmetry properties here. Now, remember isotropic tensor that we talked about? Looks like this, and because of the symmetry, we have this, and that gives us this equation for isotropic medium. And so all I've done here is I've taken that expression for isotropic tensor, and there I have used stiffness tensor. And now I'm applying a symmetry condition to the stiffness tensor to the isotropic tensor, and that gives us this equation. So here I have only two components, lambda and mu. Okay, so there are only two coefficients, elastic coefficients in isotropic medium. Okay, starting with big C. So you can just write this down in terms of stress and strain, and I will talk about this a little bit later before I'll come back to this. Now, in general, for an isotropic medium, we have this equation. So you need to expand it, and you can write down different components of taus. So for example, I can write tau 11 and tau 22, tau 12. These are some of the terms. So you have 6 of these, right? Stress. And the way it works is that we don't carry all of these 4 coefficients. We use a compact notation, the white notation. So we call this 1, 1, 2, 2, 3, 3 goes to 3, 2, 3 or 3, 2 goes to 4, 1, 3 or 3, 1 goes to 5, 1, 2 or 2, 1 goes to 6. And here you will see that we don't show. So if there are 4 components, I mean like 4 directions, Cij, Kl, so how many scalar components do I have? Stress tau Yj essentially has 3 by 3, right? 9 components. But it's symmetric. Because of that, it reduces to 6. So here we have 3 by 3 by 3 by 3. That means 81, right? But you will show that there are some symmetry properties because of which this reduces to fewer. First of all, we write this in these compact notations using the symmetry properties. Then we have a new representation. And here we have on the left-hand side, we have the stress vector. These are 6 components that are independent. They are 6. These are 6 strain components, independent components. And now I can write my 4th order elastic tensor as a matrix, 6 by 6 matrix. So this matrix is not a tensor though. It's not a second rank tensor in 2-dimensional space. It's actually a 6-dimensional space. It's actually just a matrix that is representing your 4th rank elastic tensors. Okay. And here, because Cij, so this one basically 6 by 6. So now it reduces to 36, right? So if we imply the symmetry condition, then this reduces to this. So that means this is now 21. Okay. So in general, we only have 21 independent elastic constants. Okay. So this is the most that you can expect. in a general anisotropic medium because of the symmetry properties that we have. Okay, but the anisotropic is a special case where you have only two. Then we can actually transform these matrices using some orthogonal transformations. So this basically is a matrix that can be applied to get to the new coordinate system. And again, I will leave this part. So this is the most general anisotropic media, which is a triclinic system. Okay. And this has 21 independent coefficients, which we almost never deal with because there are too many parameters and seismic data does not have enough information. And also, I'm not sure if there are any subsurface formations that behave as triclinic medium. Then there's this monoclinic symmetry. And this is what the monoclinic symmetry look like. If you have X3 is the symmetry axis or symmetry plane, they have three symmetry plane of symmetry, X3, X1, and X2. And given that, you get this kind of stiffness tensor, stiffness matrix. Okay. Then we have orthorhombic. In orthorhombic medium are somewhat common in seismic exploration because if you have two fracture planes that are orthogonal to one another, that can be represented in as an orthorhombic medium, and the number of stiffness coefficients is 9. Okay, so here now we come to our hexagonal symmetry, which is the VTI medium. So there is a vertical axis you can rotate, and this is azimuthally symmetric. And it turns out that for this, we only have 5 stiffness coefficients. Okay. So this is also C44. I think this got cut here. And these actually correspond to certain direction of propagation, and I will talk about those later. And if you take that and rotate it but 90 degrees, that becomes a TTI medium. So all this you have done is you have just rotated the medium, and this is what the matrix looks like using those orthogonal transformations that I talked about earlier. So you can start with the full monoclinic system and apply symmetry conditions, apply rotations, and then you can go to the special cases of anisotropic medium. So what we have is we started with 21, then we have 9 for orthorhombic case, then we have 5 for VTI case, and then we have 2 for the isotropic case. So going from general anisotropy to isotropy, we have two coefficients. Okay. All right.
So this VTI, what we call, is because of sand shale layering, what we call it.
Yeah.
Is it
So
because-
yeah, sorry, I didn't talk about that. So I didn't mention any of the. So what is VTI? So the kind of anisotropy you're talking about is called effective anisotropy. So you have a thin layering, or if you have a shell layer which has got thin planes, in the seismic frequency band, they behave like a vertical transversely isotropic medium. Okay. So this is the stiffness tensor, but doesn't mean anything. Or stiffness matrix, it doesn't really mean anything unless I relate it to the data, right? And we'll talk about what is the effect of this. What is the implication of say VTI medium when recording the seismic data? Okay. What this means is that the velocities in the vertical and the horizontal directions are different. Okay. So that poses a serious problem, because what happens is that if we assume that the medium is homogeneous and isotropic, then the reflection gives you a hyperbola, right? But when there's only one velocity, right? But in case of VTI medium, the velocity is changing with direction, And from going from vertical to horizontal direction, the velocity is changing. So that means this may have, this becomes non-hyperbolic. So if you use just one velocity to apply NMO, it's not going to get flattened. Okay. So it will leave some residual that looks like a hockey stick effect. And that can be only corrected for using VTI parameters. Okay. And this can also happen if you have horizontal fractures. And HTI can be because of vertical fractures, and orthorhombic can be because of two orthogonal planes of vertical fractures. Okay. Okay, now let's come to the equations of motions. So there are two fundamental equations that we have in seismology. Okay. One is your Newton's law, and the second one is Hooke's law. Well, stress comes here, right? I plug it in there, and that's our wave equation. That's it. And this is a wave equation for in 3D inhomogeneous anisotropic medium, right? So how would you make it anisotropic and damping? Anybody?
So we have to add another term, sir, with the
Exactly.
yeah.
You have to add another term here, right? With the viscosity part. Yeah.
Right, yeah.
Good. Thank you. Very good. And then your wave equation changes accordingly, right? So very simple derivation of wave equation. People say, oh, you don't know wave equation. Well, you do, because you know Newton's law and you know stress, you know Hooke's law, right? So you know wave equation. So in initial notation, this is what it looks like. Now let's look at different forms of it. So this is our heterogeneous anisotropic Earth. So I put in the constitutional relation. I've not put damping here, and that's my wave equation, right? This reason it's inhomogeneous is because the C elastic coefficient is inside the derivative term. If you want to make it homogeneous, then it can come out of this, right? Because the derivative with respect to C is 0. So in general, the number of variables that we want to compute is 6 components of stress and 3 components of particle displacements. Okay, so here, at this point, I want to tell you one other thing, is that this is definitely wave equation, but sometimes we just use this first order equations only. And the first order in the sense that I can take this, and if I remove one dot, this becomes my velocity, right? And then you can put a corresponding dot here, and then you can also change this. So you can keep these as separate equations. So first you compute stress, then you compute, first you compute stress, then you compute displacement, or first you compute displacement, then stress, and then you can simulate both stress and displacements. Or you can substitute stress in this equation and get one equation where we simply compute displacements, okay? And then what happens is that you have to deal with, in general anisotropic medium, you have to deal with 21 coefficients and of course density, okay? So you have 6 components of stress and 3 components of particle displacement. So that means we have 9 variables in the coupled system or full wave. And if you just want to stick to this equation, you have only 3 components of displacements. So initially people thought that this would be cheaper because we're only computing the displacement, but then it turns out that we can come up with some clever algorithms with this first order system with velocity and stress, and that gives us a staggered grid system, which is actually got certain important interesting properties. But we'll
so
leave
there is
it.
a question, sir, here, slightly off topic, but still it is very relevant. We have, let's say, 21 elastic coefficients coming from Hooke's law. Maybe it will drop to some few parameters, 3 in VTI. And the another one is the density term, which is coming from the, I think, from the Newton's second law. But still, why it is very difficult to derive density out of all this? Let's say if we compare lambda, mu, and density, it is only density is always problematic. Why is it so?
Yeah, so because we have limited data, right? Because you have to see what is the sensitivity. These equations don't tell you what is the sensitivity of seismic data to different parameters. Okay, so in general, all of these parameters affect your seismic data, right? C and all of these C components and rho should affect your parameters, including your damping term. But we make some approximation first. And second thing is that, so why is density? Because most of our measurements are single component, okay? And generally a single component and small offset, okay? So single component and small offset. And if you have single component, small offset, you cannot get very good estimates of density unless the density contrast is very large, okay? Not only that, the kind of method we use in inversion also limits us to estimate density. For example, if you're using simple two-term AVO equation or three-term AVO equation to estimate density, the linearization itself assumes that the density contrast is very, very small. So you don't get that. So density effects coming in a large offset. Other thing is that if you have multi-component data, then we can better resolve density. So this is a perfectly valid question. The reason you are not able to get density is because we have limited measurements. Okay.
Okay. Yeah. Thank you.
And use of incomplete theory. Okay. Any other question? Okay. Yeah. Anytime you have question, just interrupt me. Okay. So now I go to my same equation, but I reduce it to isotropic case. So in isotropic case, your stress strain relation becomes simpler. I have only lambda and mu, right? Not 21 coefficients. If I have that, then my wave equation looks like this. So I have lambda plus twice mu. This is the gradient of divergence of u. This is curl of curl u. And there's a gradient of lambda. This is a gradient of mu, right? Now this is the set of equations that we solve when we're simulating wave propagation in elastic medium. So here still we have 6 components of stress and 3 components of strain, but we have only 2 elastic coefficients and density. Okay. Now, as such, if you look at this equation, this divergence represents push-pull motions. This is basically P waves, and this basically represents S waves. But in heterogeneous medium, P and S waves are not completely decoupled, except for at high frequencies. So you can reduce this to isotropic case. All that you have to do is to get rid of, this is 0, right? Grade mu and grade lambda. So that this becomes 0. This term goes away. So this is your equation for isotropic. And for homogeneous medium, I'll come to that later. Now what we use is a constant density acoustic medium. So here we set mu equal to 0. And I'll show you a simpler derivation later on. And then we get this, and this is our velocity. So we have only one variable, scalar parameter, could be pressure, and only one model parameters. This is velocity. So what you see here is we have 21 plus rho, then we have 2 plus rho. Now we have only 1 plus 1, not even rho. And this is the most common wave equation that has been used in exploration seismology. So you can see what kind of approximation we have made. We could typically most general form is viscoelastic, anisotropic, and heterogeneous. Anisotropic, heterogeneous, viscoelastic, and laterally heterogeneous, elastic and laterally heterogeneous, acoustic and laterally heterogeneous, constant density and acoustic heterogeneous. Then we have another form called acoustic BTI medium, which we'll talk about, which may not talk about in details. And then we have some stratified medium. So you can see that we have different level of approximation as you go from top to bottom, right? And the most common one is this. This is the one we have been using for many years, right? But despite all of these approximations, we have found oil, right? Why? Should not work, right? If you give it a mathematician, he'll say, oh no, this is nonsense. Anybody?
Because initially we started with stack data, which is just an acoustic representation, right? So when people looked at bright spots and all those, that was just a stack data, no AVO and all those. So it was essentially an acoustic representation of the wave.
Yeah.
And then
So,
also with and also with small offsets, we have certain approximations valid.
mhm, mhm. You see, the one of the things that you recognize is that all of our traditional work involved travel times, right? Of P waves. And for that, acoustic medium actually approximation works really well. And for when you have small offsets, you're absolutely right. But now, since we want to find out more details about the subsurface, we want to go deeper, we want to go broader, we are trying to relax those approximations slowly to get into a more realistic or more physics honoring wave propagation models. So you were right. Okay. So do you guys, I mean, the students, do you recognize this? You know that this gives us some results which are quite useful, but now we have to be more ambitious because we want to find out more complex structures and scenarios. Okay, a little bit on very simple description of seismic waves. Okay, so that's our constant density acoustic wave equation, which I talked about already. So let's look at the simple solution of this partial differential equation. Okay, this is a sine wave, sine function. So A is the amplitude, omega is the frequency, and f is f is frequency, and omega is equal to also 2 pi f. Okay? So and k is the wave number, and phi is the phase. So very basic physics tells you v equals f times lambda, and f equals 1 times period, and k is equal to. So this is your wave number, and this is your temporal frequency. And if you draw these sine functions, you can see that from peak to peak, this is a period, and this is our wavelength. Okay, in x. What is time? What is period in temporal domain is wavelength in the space domain. So we'll be using these terms quite often. And this shows you how this function looks like as a function of x and t. You can draw it yourself. So this tells you, how the frequency and wave number representation looks like. This I already talked about. Okay, so that's our heterogeneous medium. And if I set mu if I set this term 0, because if it's a homogeneous medium, then the spatial derivative of lambda and mu, that should go to 0, right? So this is 0 and that's 0. That gives us wave equation for a homogeneous medium. And here have this term and that term. And if you divide by rho, this is your what we call square of p wave velocity. This is square of shear wave velocity. And this term represents your p wave, and that represents your shear waves. So the kind of waves that we'll be dealing with are p waves, shear waves, and explosion seismology will also sometimes see Rayleigh waves and love waves, converted waves. They're converted at the interfaces, PS, SP, and the multiples thereof. So what are they? So seismic P wave is a compressional wave, and that propagates the fastest. So this is what it looks like, the compressional wave propagation. Okay. You can also see how the compressional wave propagates in 2D. This is that part, first part of that wave equation. And you can also present it in ray diagram. So this is your source, that's your receiver, and you can actually see how the ray propagates and reflected from this particular boundary. And you can see that we have drawn the arrows forward and backward because it actually takes the same time, and it turns out that it has the same amplitude because of reciprocity. Okay. And the wave propagates along the direction of the ray for isotropic medium. And the particle polarization is also in the same direction. Now, if you look at shear wave, the displacement is orthogonal to the direction of propagation. So this is what it looks like. The wave is propagating in this direction, but the displacement is orthogonal to it. This is what we call SV mode. And I can see that this is your ray path, and these are the particle motion diagrams. Yeah. Now, the SH wave is also orthogonal to the direction of wave propagation, because when 3D, when the wave is propagating, this is along the ray, but the not orthogonal direction could be in this plane or plane perpendicular to it. The one that is perpendicular to it is the SH waves, is the horizontally polarized shear waves. In isotropic medium, they propagate with the same velocity. Okay? So this is our isotropic Hooke's law, and now we can show that these terms you can divide by the density, and they correspond to P and shear wave velocity. This block is the shear velocity, this is the SH part, and this is the PSV part. Okay. So now you can see in isotropic medium, this is what the wave fronts look like. The shear wave front is slower, and this is your P wave front. And then we have Rayleigh waves, which are actually horizontal, they propagate along the surface. And this is the kind of particle motions they have. This is what the Rayleigh wave motion looks like. Okay, so to summarize, you have P wave, which is compressional. This is shear wave, which is normal to the direction of propagation. It could be on the plane or normal to the plane. And this is your Rayleigh wave and love wave. So the characteristics of seismic waves, to summarize, the P is the primary, what you call primary or compressional, a longitudinal wave, this body wave. And typical velocity is 2 to 7 kilometers per second in typical Earth's crust, and greater than 8 kilometers in mantle and core. P motion travels fastest in materials, So these are basically the first arriving energy. S is the shear wave, and the velocities are slower, depends on the lithology, but typically 3 to 4 kilometers in typical Earth's crust. But for sediments, we have different ranges. And sediments are what we deal with mostly in many of the exploration applications. And one important thing is that S waves do not travel through fluids. And if you notice, Vs is equal to square root of mu over rho, and mu is equal to 0 for shear, and therefore the shear wave velocity is 0, and that means that shear waves do not travel through fluids. And then you have a little bit about Love and Rayleigh waves, and you can read from this. And just to summarize this particular lecture, we focused on small elastic deformations, and we used Hooke's law for linear regimes. We also showed you, viscosity tensors for wave attenuation. And one thing that I did in detail is comparison of isotropic and anisotropic media in terms of different forms of the stiffness tensor. We went over detailed 21 independent elastic coefficients, and we distinguished between compressional P waves and shear S waves. So with this, I think this concludes this particular lecture, and I have some short ones. So can we take a short break before that? Are there any questions we can take? Okay. Any questions?
So I don't think people have questions. So how much time is left, sir, for how many lectures are left for today?
Basically one and a small part.
Okay.
Is that okay?
Yeah, so I think we can continue, sir. If it is a small one, we can continue and finish it. Of course, if you want a break, then you can take a break.
I just need a 2-minute break, okay?
Okay, sir. Okay, yeah.
All right, so I wanted to go a little bit detail on the anisotropy stuff because that's important, and this is modern, and you wanted to be equipped with handling data that has an isotropic effect that you want to include because you have large offset data. So the basic thing that we'll start with are the stress tensor equation and the wave equation. And this is the wave equation without the source term, and then this is what we have in the initial notation. So we'll follow Cartesian axis system. We've already talked about that. Okay, so to describe anisotropy, first we need to look at this concept of plane waves. And earlier I did introduce you to plane wave, but since we're talking about anisotropy, we'll add a little bit of complexity to it. So we'll define the plane wave using this equation, which is not different from what I had earlier, except that this is a vector now, and this vector D is the polarization vector. Okay, and this L here is the direction of the plane wave. So let's say that these are the wave fronts in a plane wave of state. So the plane wave is one which basically has a planar wave fronts, right? Now and the wave propagates normal to this in general, as we understand from isotopic media. And for P wave, it's the particle is polarized along the direction of the wave, and for shear wave, it's normal to it. But here, what I have done is I'm representing the direction with this L, but the particle motion direction I have given as D. And in general, they don't have to be parallel or perpendicular, especially in anisotropic medium. Only in isotropic medium, we know that D dot L is 1 because your P wave is polarized along the direction of propagation, and shear wave is normal to it. But this relationship is not true in general anisotropic medium. So you don't have pure P wave or pure shear wave, and that's why in anisotropic medium these are sometimes called QP and quasi P and quasi S waves. So with that, if I substitute that into the wave equation, that gives us a matrix equation, and the determinant of that matrix equation would give us this P, which is P here is nothing but slowness. Okay, so P is the slowness, which is reciprocal of phase velocity. Okay, what I mean by phase velocity is the propagation velocity of the plane wave. Okay, so this is essentially 1 over phase velocity. Okay, so in general, you can solve this equation, which is called Christoffel equation, and that gives us solutions for P, and that gives you the velocities. Now, this is probably not that important for isotropic medium because you can show that that for isotropic medium, this goes to simply shear wave and P wave velocity. But this becomes a bit more involved when it comes to anisotropic case. So let's look at the VTI case. Okay, in the VTI case, this is my fourth rank isotropic matrix. From there, I get this Christoffel equation, and this is my characteristic equation. Okay, so we need to solve this. This is a matrix, determinant of a matrix, and clearly we can decouple this from this. So this gives you a scalar solution, and this gives you so this is for PSV and this is for SH. Now, what happens is this gives you solutions of quadratic equations, but here we can solve these, and it turns out that you can solve it for different directions, right? For putting in different directions. For theta equal to 0, we get 3 phase velocities given by P1, P2, and P3, C44, C44, and C33. Then we have theta equals pi by 2. So we have C66, C44, C11. Theta equals pi by 4. It's actually a combination of these. So what it basically tells you is that for VTI medium, your velocities are dependent on directions. So these are in particular directions. But in general, you can get the solution from this equation. Okay. Now, if you solve this, this is a quadratic equation in P squared. That means it will give you 4 solutions, but then one is for upgoing, one is for downgoing. Okay, so what this means is that for vertical propagation, SH and SV, they propagate to the same phase velocity. For horizontal propagation, P, SH, and SV propagate to different velocities. And for all other angles, the velocities are angle dependent. Now, I want to be a bit cautious. When I say P, SV, and SH, these are pure mode. And they are in pure mode only when they're propagating in these particular directions. In other directions, they are not pure P, pure PV, and SH. These are what we call quasi. But they are orthogonal. So based on this, then Thomson actually modified the coefficients. Remember, we have C11, C33, C44, C66, and C13. These are the 5 coefficients for the VTI case. Now, Thomson took these based on these phase velocity equations, came up with representation in terms of velocities, and he showed that I can now use something called alpha naught, beta naught, epsilon, gamma. Alpha naught corresponds to vertical P velocity, beta naught corresponds to vertical shear velocity. Epsilon is the percentage of P anisotropic because it's the difference between C11, C33, normalized by C33. And here we have then we have gamma, which is basically the percentage of shear anisotropy. Then there is this term called delta. And this delta is a bit complicated equation. Then he simplified it further to get to delta star using weak anisotropy. So now we have 5-parameter representation. And the reason this became very popular is that when you write C11, C3, C44 and all this, you have no clue but what is the velocity here, right? But when you relate it to these parameters, this tell you that they are related to certain velocities in certain direction. So C1 by C33 by rho, square root of that, is vertical velocity, but C11 by rho, square root of that, is the horizontal direction p velocity. Okay, and that is why it's very easy to now interpret the data using these parameters. And you can now look at your seismograms and you can say that near zero offset we have vertical velocity, and we go to large offset we have horizontal velocity, and in between the velocity is given by that equation which involves delta. So your NMO is not going to be purely hyperbolic. It can have non-hyperbolic components. Okay. So a little bit about phase and group velocities. So the one-dimensional wave equation is this, and its solution is a plane wave, which is given by that. And you can just substitute in there, and that gives you solution that yes, indeed, it satisfies wave equation. And I already talked about this. So here we have an argument of waves. So when you have these peaks and troughs are matching with each other, it's called in phase. And the peaks or troughs are not matching, this is called out of phase. Okay, this could be in space or it could be in time. So group velocity is then given by, the velocity is lambda over f. So group velocity is given by omega over k. And this is also, yes, omega over k, okay? Now, the group velocity is combination of different components. So for example, I have one plane wave with kx minus omega t, but another one is perturbed by k plus delta k, omega plus delta omega. Now, if you do simple algebra, what you see is an equation that looks like this. So there is one cosine which is propagating with this velocity, phase velocity, this frequency, another one that is propagating with this velocity, phase velocity, and this frequency. Now you can define something. So it means that individual phases are propagating with different velocity, but there is an envelope around it that is propagating in a different velocity, and that is called group velocity. And that is given by this equation. So delta omega by delta k. And I'll show you what the implications are. So if you follow this, you can see that red dot is propagating with group velocity. And now you can see black and red. Black dot is moving with phase velocity and red dot is moving with group velocity. Okay. So my question to the group is, when you measure seismic data, which velocity are we measuring? Okay, you have seismic data, you fitted a curve and you got the velocity, right? What velocity is that? Is it group velocity or phase velocity? Anybody wants to volunteer?
Let me make a guess. Phase velocity. I may be wrong.
No, actually, you are measuring group velocity because the groups are the ones that you are measuring. Okay, you don't measure individual components. Okay.
Okay.
Now, this dispersion could be depending on the velocity being different for different plane waves, like it happens in anisotropic case, or it could be for different frequencies. Okay. So it's very important to understand that when we're measuring actually group velocity, but then reflection coefficients are functions of phase velocities. Group velocity is same as phase velocity. If there is no anisotropy, no attenuation. Okay, so that's why we don't make a distinction. But when you bring in attenuation, when you bring in anisotropy, then it becomes very important that you distinguish between group and phase velocities. Okay, so for the anisotropic case, we can do a little bit of algebra, and you can show that group and the relationship between group and phase velocities. I will skip that part, but I'm going to show you some interesting pictures. Okay, here we have Green River shell, which is anisotropic medium, right? So here I'm showing you the slowness diagram. Okay, slowness means reciprocal of velocity, phase velocity. So this is your QP. This is P velocity, quasi P. Now tell me, if this was isotropic, what would that look like?
Be a circle.
It'll be a circle. Very good. This is QS1, which is essentially close to SV, and that one is SH. Okay. So here you can see a very interesting character. This is the shear velocity is not the same. It may be a slowness. It's high here, low there, and so on. Similarly, P wave is not the same, and this is your SH, which is more it's actually elliptical. In 3 dimension, this is what it looks like. But when you transform this to group velocities, it becomes even more interesting. The P wave shape has not changed, but what you see in shear wave are these triplications. That is because of the way this is changing, okay? And these triplications would mean that there's more than one arrival in shear waves, okay, in the anisotropic medium. Even it's a homogeneous medium. There's no reflection, okay? And there you can get these triplications. And one thing that you notice here is that the velocities between say SH and SV, this is P, I'm sorry, this is because this is now in velocity domain. This is P wave velocity, this is your quasi S1, which is SV, and this is quasi S2, which is essentially SH. So you can see that in isotopic medium, SH and SV velocities are the same, but here it depends on the direction. And that is why you see something called shear wave splitting, okay, in the anisotropic case. So that becomes very, very important. Okay. Similarly, we have group velocities for other kind of material. This is for a fractured medium. So now this picture has completely changed. This is an HDI medium, and you can see what that slowness surface looks like and what that group velocity looks like. And then these are for quartz, and this has even more complication. You can see that how it looks like. It's very, very interesting to plot these and see what they look like, and then understand how the wave propagation can be so complicated even in homogeneous anisotropic media. Okay, and this was for something called stishovite, and these are for special crystals. Like this is for silica, that's for MgO, and this is for perovskite. So to summarize, we have gone through some foundation materials, elastodynamic propagation. In plane wave propagation in anisotropic media is fundamental to understanding the details of kinematics in anisotropic media, and for which Christoffel equation is what we use. And the solution gives us propagation direction, and also gives you slownesses that can become, of course, phase velocity that can again be mapped to group velocities. And VTI symmetry is a special case, and that can be represented by using only 5 coefficients, C11, C33, C44, C13, and C66. And these can be related to velocities in certain directions. And using those, Thomson actually came up with his parameters like epsilon, gamma, delta, alpha naught, and beta naught, which has now become pretty standard for studying anisotropic VTI medium. And then we have uh, derived an equation for phase versus group velocity. And that is given by this. And this is what is normally used in generating those pictures that I showed you. And the understanding is that group velocity is always normal to the slowness surface. And similarly, slowness direction is normal to group velocity. And we've given you examples of Green River shell, quartz, and some mantle materials, which for exploration geophysicists probably not important, but it's important to understand the whole Earth. And this shows how strongly the wavefront shape and ray direction can depart from isotropy. This is very important. Okay. So that kind of concludes this talk, and I want to leave a little bit of time for discussion. So if you have any question, comment, let's try to open up the floor.
Yes, sir. You talked about constant density wave equation. Normally, we start FWI with that. But
Yeah.
isn't that fundamentally incorrect that we are assuming density to be constant and then solving it, and we are getting results as well? So how do we
Yes.
explain that?
Because of the fact that we're overall matching the travel times much better. But when there is a strong variation in density, you can see an imprint of density on velocity. That happens. Okay, you'll see that in many data sets. So in which case you have to put a variable density acoustic wave equation. And also, if there is a converted wave, because an Earth is elastic, it's not acoustic, you have an effect of that. So these are some of the factors that are ignored. But for first cut at the velocity model, I think FWI gives reasonable results. But if you want to go into details of does it preserve AVO? That's one big question I have with the many people say it does, but it's hard to believe that it does preserve AVO. And that is something needs to be investigated. So that is why nowadays the state of the art is to use elastic FWI, and then get to the reservoir parameters from there. So acoustic FWI is most useful, in my opinion, to get more high resolution velocities, PY velocities, which you cannot get from simple migration or from standard velocity analysis. It actually adds a lot of details in the velocity model, but then you have to be careful about how you are handling the data, so that whatever you are ignoring, you have to make sure that that is not putting in some imprints on your images of the velocities. Okay. So
Yeah.
one way people do that is simply normalize the traces and only go after the phase term.
So do we tweak with the norm, sir? Let's say when you're using an acoustic FWI, but still we use the L2 norm, or we tweak with the norms as well?
Oh yeah, we tweak it the norm, L2 norm, and also like what goes into L2 norm. Is it just data minus synthetic data, or is it envelope minus envelope, or is it normalized traces, and all the different ways we do that. And it could be a combination of norms, like it could be L2 norm combined with L1 norm.
Okay.
Of the model misfit. So there's a bunch of ways we actually play with the loss function. Yeah.
Okay. Yeah. So anybody wants to ask questions, Santosh or JP?
Nothing from my side, Ash.
Anybody else interested? You can ask.
I hope I didn't put you guys to sleep.
In fact, I could recall the things which I studied in on my bachelor's degree, but we have
Yeah.
lost it. We were all taught about the ray diagram, and we have lost all the waves in between. But now we are getting it back.
Yeah, I think
So
it's important to actually, that's one of the reasons, I assume that, it's important to recollect all those before we talk about the wave theory in detail.
yeah, right. Sir. I mean, there are so many things going into an isotropy. I was just assuming that there are epsilon, gamma, and delta, and they are
Yeah.
taking care of all the things. But there are differences in the phase and group velocity that I mean, I didn't know about it. So that
Okay.
was a new thing for me.
Yeah. Mhm. Okay, then we meet next week. Is that okay now? Or if you
Yeah.
have any other question?
So I think there are no questions now. So if they have any other questions, then they can ask next week.
And also they can send me email, in the meantime, in
Okay.
between.
Okay. Yeah. That would be
So
great. I mean, if anybody, if you have any questions, fundamental questions, maybe you're not comfortable to ask here, you can ask sir. He's very
yeah,
helpful and he will reply surely.
yeah, I'll be happy to reply. And then, we can start with those. And if you think you want to start a little early, that will be fine too. I don't know.
Yeah, yes, we can start early as well. If they want to start at 6, we can start. I will ask them and then I will change the timing.
Yeah, because that way you can have a little bit longer discussion. I know you guys are probably hungry, so
Yeah,
dinner time. So
yeah. Okay. Thank you, sir. Thank you for your
okay,
time, and then we will meet
okay,
next week.
yeah, sure.
Thank you,
Okay,
sir. Bye bye.
okay,
Bye bye,
bye
sir.
bye. Bye.